Okay, guys, so I'm sorry I'm not here for it, but this is our first official lesson of physics after doing our lab. We're going to be talking about, especially in this first lesson, a lot of the things that we explored in our buggy lab, and kind of making sure that we understood everything we learned from that lab. It's going to be a lot of filling in the blanks to start with, a lot of vocabulary we got to get out of the way. Um, your assignment's going to be very easy because of that. It's just really making sure we're understanding these concepts. So let's go ahead in our first lesson here. Just quickly, this is Unit 1. It's called Kinematics. We're going to talk about what that means. But in the textbook, Unit 1 is comprised of Chapter 2 and parts of Chapter 3. So, but we're going to call this all Unit 1. So don't get confused by that. The unit numbers don't necessarily line up with the chapter numbers for our textbook. Okay, let's talk about our first unit, what kinematics is. So kinematics is the study of the description of motion, right? So this first unit is going to be all about how things move. It's a lot of what physics is, but in particular, this unit is going to be dedicated to linear motion, which is one-dimensional motion just in a straight line. Duh, right? We do talk about projectile motion at the end because we're able to break that down into straight line components at every point in its trajectory. But other than that, this is just literally traveling in a straight line, no swerving or anything. A couple things we need to get out of the way again as we talk about anything, but starting off here, you will see occasionally some of these words. System is a collection of objects that interact with each other. Now, we have two kinds of systems. We have a rigid or not rigid, basically. Rigid means it's all connected. If one part moves, the rest of it moves, right? Like a car is typically a rigid system. It just moves together. But for example, if I had a car and it was towing something behind it with a rope, if that front car were to break, that thing behind would continue to move and slam into it. So we call that not rigid. Or your body is not a rigid system because it can move independently. I can move just my fingers and not the rest of my body. So a rigid body, if one thing moves, everything has to move. A not rigid, individual pieces can move. One more term here, and then we'll kind of put all why these terms here are all important together. Is center of mass. So we can treat a system, which again is just a collection of objects that interact with each other, as a single object, as just one thing. With the center of mass, if we don't care about how the individual parts are moving. So again, a human body is not a rigid system. When we run, you move your arms separately from your legs, and I can, if I want to, stand in one place and just move my arms. However, we can treat the human body as a rigid system, as a single object with just my center of mass here, because we don't really care how my arms are moving if I'm running. I'm just caring how my body goes overall, how fast my entire body is going. In particular, how fast my center of mass is going. That's what we're going to be referring to. So that happens a lot of times where we might have connected objects, but we can think about it as just one object if we really don't care how the individual parts move. As long as they basically move all together, we can call it a single object. That's going to become more important later. So let's talk about different types of quantities that we have. So we have two different types of quantities. We have what's called a vector and a scalar. A vector quantity has two descriptors. Magnitude, meaning like a number for how big it is, and direction. So a vector quantity most importantly tells us direction because a scalar quantity only tells us magnitude. So again, magnitude specifically refers to the size, the amount, the number, whatever associated with that quantity. Where direction can refer to either if it's a positive or a negative. So we might be traveling in the positive direction, might be traveling in the negative direction, or occasionally the angle. If we're talking about projectile motion, the angle will tell us the direction. So again, vectors describe both. A scalar only has magnitude. So an example of a scalar quantity is the mass of an object, right? The mass, how heavy something is, typically is what we think about, right? Knowing the definition of scalar Why is mass a scalar quantity and not a vector? Well, it can't have direction. I can't say, oh, I have negative mass or I have mass at this in this direction. That doesn't make any sense. So certain quantities like mass, are just going to be scalars. They don't tell us any direction. But an example of a vector quantity is force that we're applying to an object. So thinking about the definition of vector, why would the force I apply to an object be considered a vector? Well, I could push forwards, I could push backwards, I could push sideways, I can push at an angle, all with the same magnitude force, but the direction is going to very drastically change things. So again, magnitude, direction, that's a vector. If it's just magnitude and it has no direction, that's a scalar. So let's talk about one of our first super duper important quantities that's going to come up over and over again, and in fact, it already has because we did our lab on it, is position. Position is the location of an object in regards to its origin. So we talk about position in general, and then we can get more specific about it. Now, typically position has magnitude and direction. So we call this a what type of quantity if it has magnitude or direction and direction? It's a vector, right? If it has direction, that's a vector quantity. So we can talk about distance, which is along your traveled path. So if I'm going up a windy hill, something like that, doing these switchbacks back and forth, if I were to measure with a measuring tape, whatever, along my traveled path, that would be the distance. Because of that, it has magnitude only. So if it only has magnitude, what type of quantity is it? A scalar quantity. If I just say, oh, I traveled 50 meters, that's just distance because we don't know which direction you were going. And it really doesn't tell us how far away you are from home. You could have traveled 50 meters like this, back and forth. You could have traveled 50 meters straight. So it doesn't really tell us exactly in relation where you are in relation to home. Displacement, however, does tell us where you are in relation from home from start to finish. So if you travel this windy road here, if we were to draw a straight line connecting you from where you started to where you finished, that's displacement. As well as not only is it that straight line connecting us from start to finish, but it also is going to tell us or needs to tell us for it to be displacement, the direction. So it has to be a vector. So in order to say displacement, I need to say something like, I traveled 50 meters directly north from here. I may have again, woven back and forth along my path, but I ended up 50 meters straight north. That is, again, displacement. That's the difference between displacement and distance. So the units for position are just going to be in meters. If we ever see anything in kilometers or centimeters or millimeters, whatever, we have to make conversions to meters for everything in our calculations to work out. And this is confusing. I am going to start doing this now. I said in the lab, you could use D for talking about the distance that your buggy traveled, the position. But typically, position is actually X. That can be very confusing because when we're going to plot it on a graph, it goes on the y-axis, but X is actually position. So again, here's a picture of the difference. Here is my distance traveling from A to B. The straight line is what we would call our displacement. So let's make sure we understand the difference. Let's read this question here. Let's say that you started at school, you walked 200 meters to QT, then 5 meters to the taquito stand, then another 3 meters to the cash register, then 100 meters out to 19th Ave before you started feeling guilty about skipping school and decided to go backwards 300 meters to where you started, just in time for first hour. What is our distance here that we traveled? Go ahead and read through it again and try it. Well, your distance traveled is adding all of this together, right? Distance is everything you have traveled. So 200 plus 5, I keep forgetting I can use my finger for this, plus 3, plus 100, plus another 300. Let's see what we get here, 608. So the distance you traveled is 608 meters. But about your displacement, reread the questions carefully. Something here tells me my displacement from start to finish. what is our displacement? It's going to be 0 meters. That's because right here, back to where you started. If you go all around and then come back to where you started, your displacement is 0. That doesn't matter. From start to finish, that's what we care about. So if you come back again, that's 0, even if your distance is something massive like 608 meters. Very important to understand the difference between those two. If they're asking for distance, they're asking for displacement, you have to pay attention to that. Now, something else you'll have to pay attention to is where our origin is going to be placed at and the direction of positive. What this means is, let me tap here, there we go. We can actually choose our direction of positive. What did I just do? Well, my camera went away, but I think it's still recording. Okay, I'm gonna keep going. I'm not sure why my camera went away. Oh well, don't know what I did. Going on, so we can choose our direction of positive, and we also need to note it, where the origin is at, again, as well as the direction of positive, because we can choose it. Here are some examples of different choices for where our origin is at. That's our starting, where we determine our position to be 0 is what we're referring to in this case, as well as different options for the direction of positive. So for A, notice that they chose X to be 0, kind of right here on the left side. Now, that's X equals 0, that's our origin, our reference point. However, our starting point, x1 over here, is at -10. Our ending point over here is +40. So if I'm going from -10 to +40, what is that distance I traveled? Well, what you can do to find that is subtract our final point, which is x2, minus our starting point, and then take the absolute value of it in this case. So we have 40 minus a -10. Well, this works out to be positive anyways, so that gives us a distance of 50 meters traveled. And you can see that across the top that from start to finish, we have 50 meters. Notice that's going to be the case in every pool scenario, that the length of the pool is 50. So doesn't matter what they do to change the direction of positive, or if they change the origin. In each of these cases, our distance is going to be 50, because direction doesn't matter, origin doesn't matter when we're talking about distance. It's just how far did you go? It doesn't matter anything else. Displacement, though, needs to be relative to the direction of positive. So notice up top here, they have said that going to the right is the positive direction. So if this is our start and this is our finish, notice that we traveled in the direction of positive, right? To the right. So we're going to say our displacement is also positive. From start to finish, our displacement is a positive 50 meters. You don't have to write the positive. Obviously, if you leave it off, it's inferred to be positive. But just to differentiate here that I am explicitly saying that we traveled in the positive direction. Looking at B now, they have still said that going to the right is the positive direction. But notice how they labeled x1 and x2. Our little swimmer here is now traveling in the direction opposite to what we chose to be positive. So our displacement from start to finish, since we traveled in the opposite direction, is now going to be -50 meters. From start to finish, we traveled in the negative direction, so that is going to be our displacement, -50. Looking at these next two, I want you guys to determine what our displacement is based on start to finish, the direction of travel, in respect to what we said is the positive direction. So basically, is our displacement here going to be positive or is our displacement going to be negative? Go ahead and try it. Okay, so our direction of travel from start to finish is pointing the same direction as positive. So this is a positive 50 meters displacement. Now notice in D, even though we're starting at negative 50 meters, we are still traveling in the positive direction and ending up at 0. This is still a positive 50 displacement because we traveled in the positive direction. I know this is a little confusing. We're gonna practice this. But typically, to make things easier, we label our pictures in a way that makes sense. Usually, for most people, if we were to look at these A, B, C, D examples, which one do you think would be the labeling that makes the most sense to you between A, B, C, D? Most people are going to label it like C, where our starting position is at 0 and our final position is at positive 50 in the positive direction. The point here is that you can actually choose whatever makes sense for your situation, as long as you're keeping everything consistent, all of your signs consistent for your directions. That is totally okay. So filling this out here, traditionally, again, we say that up or right is positive and that down or left is negative, but it is your choice for what makes sense, again, depending on the situation. Let me see, where are we at? Okay, we are going to go ahead and talk about velocity and then take a pause after that, so I'm not making this a half-hour long video. So let's go ahead and fill in our notes for velocity. So talking about velocity now, our second super duper important quantity. The definition of velocity is the change in displacement over the change in time. Velocity has magnitude and direction because it is specifically talking about the change in displacement. This is not change in distance, this is change in displacement. So because it has magnitude and direction, it has to be a vector quantity. We got magnitude and we got direction. Now speed is the scalar version of velocity. So this actually is the change in distance over the change in time. So again, the difference between these two is that velocity is referring to displacement, speed is referring to distance. However, for a lot of the times right now in this unit, we're going to be traveling in a straight line. So if that's the case, they have the same magnitude because our displacement is going to have the same magnitude as distance because we're traveling in a straight line. If I'm not curving all over the place, distance and displacement, yeah, are going to have the same magnitude. It is possible still, though, while traveling in a straight line, to have distance be positive and displacement be negative, but their magnitudes will be the same. A couple different things here that we can talk about. We can talk about constant velocity, which is what your buggy was supposed to have. Your buggy was not supposed to have any acceleration. It was supposed to drive the same speed every single time. A couple of you guys had some problems with that as the batteries died. But a constant velocity is a velocity that does not change. Duh, makes sense. We'll talk more about that because there are some important things there with constant velocity that we can do. We can also talk about instantaneous velocity, which is the exact velocity at a specific time t. So if I want to know the velocity at 5 seconds, boom, what was I traveling at that specific time? Obviously, if we have a constant velocity, the instantaneous velocity is whatever that constant velocity happens to be. But if I have a changing velocity, which we'll talk about later, it's a little bit trickier to figure out that instantaneous velocity. But again, we're going to come back to that. Last thing here we can talk about is average velocity, which is the displacement of an object divided by the time interval of travel. Again, we can have a changing velocity, but If we know the displacement and the time interval, we can find the average, even if the velocity is changing. So the formula we have here, remember this, we talked about this in our introduction notes. This is change in x over change in t. That's how we read that. Or you can read it delta x, delta t. That's what the little triangle is, delta. But again, change in x over change in time. We will expand this to mean your final position, x sub fine f, minus your initial over your final time minus your time initial. My dog just tripped. Go on, Havoc, it's okay. So we can expand any of these little triangles, we can expand to be this. And velocity is going to be measured in meters per second. Once again, if we're given kilometers, if we're given hours, we need to convert to meters per second for all of this to work out. So looking at example 1 here, this will be 1 or 2 last slides and then we'll wrap up. It says a race car travels around a 500-meter track in 15 seconds and returns back to the starting line. Now, because this is a race car, we can assume that it's probably accelerating sometime during all of that. But that's okay, because we can determine its average speed by doing the change in distance. I'm going to go ahead and put d for this, over the change in time. This is a 500-meter track going all the way around. So technically, we're supposed to say our final distance minus where we started, and our final time minus our time when we started. But our initials are going to end up being 0, so we can kind of not focus on those. What is my distance that I traveled here? And then what is my time? Go ahead and put those on top, on bottom, and see what you get. Well, our distance we traveled is 500 meters because it is a 500-meter track. We did that in 15 seconds. This was a really fast car. This is going to be like traveling like a rocket. So 500 divided by 15, this is going to give me our speed. Let me pull it up here. Where is my calculator? 500 divided by 15. This gives us 33.33 meters per second. That's really fast for a car against possibly a rocket at this point. But that is the average speed. Again, it could have been changing throughout, but we can call that the average since we know the total distance over the total time. And for average velocity, now for velocity, we need specifically displacement. So let's go back and read. A race car travels on a 500-meter track and returns back to the starting line. So here's our car. It went. So what is its displacement? 0. Yes, I can say my starting position and my final position are the same. So I have no displacement here. Yes, it was 15 seconds, but that doesn't matter. Our average velocity in this case is going to be 0 meters per second. Seems very weird. You might wonder why that's even useful to us, but there are a lot of cases where we're talking about average velocity is going to be useful to us. Sometimes, again, if you're coming back to where you started, it does end up being 0. So the last thing I want to show you guys here, to hopefully you're not falling asleep, is this video of Usain Bolt. Pull up, I got 10,000 things open here. Let me see where I can start the video at. There's my sub plans, 125. Hopefully this records okay. Hey, I found start webcam. I'm back. Okay, right at the end. Hopefully you didn't fall asleep without seeing my face and all my hands moving around. But let's go ahead and watch Usain Bolt's race. His record here was a 100-meter race, is what it says, in 9.58 seconds. man. Yeah, pretty insane. I cannot even go half that speed or a quarter of that speed or an eighth. Oh my gosh. So let's talk about this. What was his average speed for this race? It's a 100-meter race. He went 9.858 seconds. Find the average speed. Well, average speed is once again going to be the change in distance over the change in time. He went 100 meters. Again, we can say 0 to 100 in 9.58 seconds. That means that his speed is about 10.44. I always have you guys round to 2 decimal places here. 10.44 meters per second. Again, super fast. That's insane. 10 meters. That's a little bit over, what? 10 meters? 30 yards? Whoa, I'm thinking that wrong. Whatever it is, it's insane. 10.44 meters per second. And average velocity, now again, average velocity, we are thinking start to finish. So here, our average velocity was 0 because it was a round track and we came back around. Here, we had his start to his finish. So what would be his average velocity here? Well, change in displacement over change in time, we are traveling in a straight line. So because of that, our distance is the same as our displacement. So we are going to have the same thing here because we're traveling in a straight line. So for a lot of this unit, we may throw distance and displacement, speed and velocity, throw them kind of around interchangeably. That's only because we're traveling in a straight line. Once we start talking about different types of motion, we have to be very specific about if we're traveling in a straight line or not. So this was a very long video, a lot of filling notes in. We are going to do the last 2 slides together tomorrow. So for your assignment, you are only going to have to do, let me pull it up, 1 through 3, and that's it. If you guys need the rest of the time to work on your lab document, finish up what you can use that.